Hey everybody, today we will do another video, and today we will continue with differential equations. It is going to be in the area of circuits because this area is application, basically it's application based, and I might just give some quick examples. Probably I'm not gonna solve problems today because of the time, but I will explain the formulas and cases that are important to understand in order to continue with this type of problems. And it's going to be problems related with, obviously, with circuits, right? Circuits. So basically, the topic is higher order circuit. So the topic is higher order circuit, but or second order circuit. So second order circuit. So that is the topic, right? However, basically what we do is apply differential equations to solve circuit problems. And so in this case, what basically we're doing is we're trying to solve differential equations, and obviously it's going to be with initial conditions, right? So because otherwise it doesn't make any sense to solve a differential equation in a real life situation if we don't have initial conditions. Okay, so basically the differential equation is the following. So we have di, we have d squared I, right? And of course in the bottom we have dt squared, right? And then plus r over L, and then dt di, right? Di over dt plus I over LC is equal to 0, right? So if you remember from my last videos on differential equation, this is already in the form of this part right here. This part right here is equal to 0, which means that it is like a homogeneous type of differential equation already, right? So what basically we will do is the following. So we know right here that we have a second order differential equation. Why? Because we have d squared and we have a dt squared, right? And then we have a variable, the changing variable, and I, and this I represent the current of the circuit, right? And then we have a constant in front of this derivative, and this, as you can see, that the order is decreasing, right? So you have a second order, you have a first order, and then of course you have a constant. And this constant right here, as you can see, Um, as you can see right there, we have the combination of both. We have an L and we have a C. The C represents capacitor and the L represents inductor, right? And I think L is inductor, right? And C equal capacitor. So basically what we're seeing is we're seeing a multiplier of L over the, and then R of course is resistance. R is resistant, right? So assume that you have in this circuit, you have something like this. So you have a voltage source. You have a voltage source plus or minus right here, and this can be, AC or DC, it doesn't matter. Normally, in this case, mostly it's AC with a little thing like this, and then you go like this, right? And then you have a R right here. If this marker was working, it would be much better. But so we have an R, right? And then we have an R, and then we have a loop, a wire, right? The resistor is more like this, right? And then right here, right? And then this is L, right? So this is RL. We still need another variable, and then we do this little guy like this, right? Capacitor, we have a negative plate and a positive plate, right? And we come over here, back to the source. So RL, and of course this guy is a C, right? RLC. RL, right? RLC. And of course you have this multiplication of these two guys right here, that these two guys are just multiplying each other. So basically what we have right here is RLC circuit equation of variables inside of differential equations. And again, let me repeat this again. We have an RLC circuit inside a differential equation, second order, right? It is based on current. Based on current, we have a voltage source right here, right? Voltage source B, but we have a current source that also goes around this loop. It goes around this loop, coming back over here, coming back, right? Of course, in order to make a source, you need three. You need resistance, you need voltage, and you need current. Other than that, I mean, you might have a source, but it's not working. It's a not working source. That, on real life, that's how it works. Okay, so that is basically the equation that we're dealing with. Now the question is how we make something make sense out of this, right? Because right now it's hard to, even though we have a numbers over here, right? I can get a number for this, I can get a number for that, and try to, but it's going to be messy and not going to be able to solve it, right? What we can do is the following. What we can do, because in this case we need to get what is something is called characteristic equation. In order to get that, we need the following. So we need to get, if you remember from algebra, that beautiful formula that says, back in your days when you were learning, the basic algebra, you remember that beautiful formula that is that is equal to x is equal to plus or minus, right? Minus b plus or minus the square root of b squared minus 4ac divided by 2a, right? So that is basically the formula in algebra, right? In algebra, right? Now, similar, we need to get something here. The only thing that we need, we need two of them normally. And also, we're not gonna deal with all this. Eventually, we probably will, but at the moment, we will do some what is called cases, right? So basically, we will have to get one that is equal to this can be derived a couple different ways, but called S1, right? Which is going to be equal to just the positive part of it, which is going to be alpha, right? Alpha instead of b plus the square root of, and then because in circuit we don't deal too much with regular variables, right? We normally deal with other real components, right? And those components are, I don't know if I told before about frequency, but one of them is called frequency and radians, right? In radians, right? So, which is equal to something called omega, right? Now, omega is in radians, okay? Omega is in radians, right? But let me see what the books call it. Yeah, the book called it omega. And also it's called omega. And also we have the other value that some books call it just A, and some books call it alpha. This book calls it alpha, which is technically another value that we get. In this case, the value of alpha is the value that we get as a value that will determine whether this is negative or positive. If it's negative or positive, but I might have to derive the formula in order to make more sense out of this, because it is kind of deep, and we don't have a lot of time to explain everything. So basically, the formula is as follows. So one of the formula is S1, right? And and then we have alpha squared minus omega, right? And omega is squared, right? Of course, gotta be both. Squares inside the square root. But eventually, it's omega naught. Eventually, I will explain more in depth how we come about all of this. But one of the things that we need to think about it at the moment, so we have an S1, right? And what happens when you do an algebra? Back in your days when you were doing algebra, normally you find two roots, right? Two roots. In other words, this has to be another one, and the other one is going to be S2. It's going to be equal to negative alpha, right? And then of course you gotta have a negative in there, right? Because I did already the plus, now it's negative, and it's going to be the same situation where we have alpha squared minus omega naught squared. Okay, so now we have the two formulas, right? Now another way to express this will be to say that alpha is equal to, so okay, and also this is radians, right? So this is radians, but normally it's radians per second, right? Radians per second. Radians per second, that's the unit. Radians per second, right? So in other words, this omega is basically rads per second, right? And that is the unit that is in this frequency, right? Because technically we're looking at a vector. Electricity work, as you can, as you know, that the light that we're seeing right now, that light frequency is at 60 cycles per second. 60 cycles per second, right? So the frequency of that is 60 times. It go like this, 1, 2, that one cycle, 60 times in 1 second. This is a lot, right? But my eyes are not able to recognize that, unfortunately. That's how the limitations of human beings, but that is another topic. But anyway, so now we can say that alpha is equal to plus, right? Plus L plus 1 over L plus R over L plus R over L, right? And also, and plus or minus. This can be plus and can be minus. Now, the question is, right? So we can represent it that way too, right? Now, can I represent this then in that? Of course I can. Of course I can. What I can do, because omega naught, right? Omega naught is equal to what? It's equal to the resonant frequency of the capacitor, which, or the combination of this guy. I'm sorry, not just the capacitor, but the combination of the L and the C, the inductor and the capacitor, right? So in this case, omega naught is equal to 1 over LC, right? Which is, that's, the generating frequency of these two guys being multiplied, right? So the resonant frequency is equal to that, right? Okay, so how we can do this, right? So now, actually this formula can be written as the following. So it can be written like this. So it can be written as, if this is positive and negative, then we can also say that S1 is equal to plus, right? Plus R over L, right? Plus this amount plus R over L quantity square minus what? Minus this guy, because technically that guy is that guy. So minus omega, but omega is not omega, it's this guy, it's LC, right? And then the square. And that is another equivalent formula. Now, the similarity with S2 is equal to minus R over L, right? Minus, right? Now it's a minus because over here I had a plus, now I gotta have a minus, right? Now, this is actually minus versus minus, because it's still the characteristic equation plays a role here. That, okay, so now we have a minus, right? Now we do the following. So in this case, the same thing. So we have R over L c minus 1 over LC and quantity squared, right? So this and that are the same. This just look more compact. This is kind of messy, but they are the same. They are just the same. Now let's talk about the cases. We talk about the formulas now, right? Now let's talk about the cases and how we come up with this guy. How we came up with that guy, because it's important to how can we make sense out of that differential equation. Okay, so we have this, right? So in differential equations, we need to make the easiest case, the easiest way to solve it, right? Differential equations are hard, and one of the ways that we can do it is by doing with the Euler's number. Euler's number is the best. Okay, so what we do right here? So I know we have a derivative. I have a derivative here and here. I don't have a derivative here, right? But what I can do is the following. So I can say that S1, or you can call it S whatever. You don't have to call it because it's just general. S is equal to a letter A, right? Actually, capital A. Capital A, E, right? E to the what? We're looking at this guys, right? You can actually use e to the alpha t, e to the alpha t. Why? Because we have a t over here, right? We have a t. We need to take the derivative with respect to time. And the changing is going to be this derivative, the changing current of those with respect to time, right? So now, how do I take the derivative of this, right? So the derivative of that is basically, when I do that, and also you can also do that, say that this is I of t, right? Take the derivative of that, right? Because that depends on time, right? Now, think about this. Take the derivative of that. It's going to be the first derivative, right? The first derivative, I think it's st. Hold on a second, what the book uses. I think the book uses st. Some books. Yeah, the book uses st. The book uses st. St, right? And also Laplace transform. If you remember about Laplace transform, you normally use s, which makes sense, right? But then this depends on t. And matter of fact, I don't even have to just call it I, and because current is equal to that, right? So I, right? Now, if I take the derivative with respect to time, right? So I say that the first derivative, di, right? di dt, right? di over dt, right? The first derivative, take a derivative with respect to t, right? With respect to t, the first derivative of that is going to be changing that variable to have something in front of that constant. And that constant is a very important, that a is a very important value that we need to understand later on. So basically, so I take this, right? Move this to the front, and the first derivative is going to be a s e to the st, right? And normally this is like tiny s like that, but I mean, whatever. I mean, t. Now this is the first derivative. The first derivative. The second derivative. Notice that I already have that. It had this first derivative. That guy had been taken care of. Now, the second derivative, d, okay, di squared di dt, I already took the first derivative, this is the second derivative, and then dt squared, right, is equal to now this guy coming in front, right, and it's going to be a times s, right, as times s e to the s, the st, right? Now when I multiply these two s's, is equal to dt, okay, d squared I, which is the changing of current on the second derivative part of it, and dt squared, right? Now, these guys get now multiplied, and I get a s squared and e to the s to the st. Okay, so that's first derivative, and we have, that's the second derivative, this is the first derivative. Now, as you can see, that now all I gotta do is substitute these guys over there. See? Now, all I gotta do is substitute the second derivative over here, and the first derivative over here, and then whatever I was equal to that, right? Just put it right there. And that's it. That's it. I mean, for the substitution part of it though. Now, so this will become what? This will become what? Will become a s square e to the st, right? Plus a constant, plus this constant, r over l. Okay, what is the second, the first derivative? It's going to be a s e to the st plus whatever I is was equal to, which this guy right here, I is right there, which is, I can actually pull this, like make it this one, right, and pull that right here, which to make more sense. So it's going to be 1 over LC e to the st is equal to 0. That's it. Now we have a differential equation that we can work with, right? Now, what can I do? Actually, missing an A here. Missing an A. Right? Now, algebraically, if you remember from high school back in the days when simplifying was very important, right? What can I do? I can do something here. I can do something to make this more presentable or more simpler to understand, right? I can actually factor this. I can factor that. I can factor the a e to the s and leave everything inside. I can factor a e and can leave the s inside. So I can say it like this. So I can say factor out a e, right? A e to the s to the st, leaving the s squared inside s plus s squared plus what? Factoring this out, I get r over l times s. That s stays over there, and then this guy comes out, and I just get plus 1 over l, and then is equal to over LC. 1 over LC, and then it's equal to 0. See that? Okay, so these are the same, but this looks cleaner, right? If you have some understanding of, then you're gonna gotta do is distribute it inside, and you get the same thing you get back to here. Okay, so now that we did this, all we gotta do right now is talk about cases. And probably not gonna have time to solve problems today because it's kind of okay. So we have overdamp. With the first case is overdamp. Overdamped case. Overdamped case, right? The overdamped case. The overdamped case imply that C. So the overdamped case imply that alpha is greater than omega. So overdamped case, right? Alpha is greater than omega, right? So alpha is greater than omega naught, right? So if you think about it, if the alpha part of it, which is alpha was 1 over LC, alpha was 1 over R, 2L, yep, I think, okay, so I think alpha, I don't know if I probably wrote it wrong, but maybe I can correct myself here, is over 2L. So if alpha is over R over 2L, then if alpha is greater than omega, right, and omega naught is 1 over LC, if this value is greater than this value, then we have overdamped case. Okay, so that's okay. Now we have that's an overdamped case. Okay, so now the next case we're talking about is a critical damped case. Critical, so that's 1. 2 is critical damped case. And the critical damped case, this is equal to 0. So this guy right here, alpha is equal to omega naught. So now, in the last case, so critical damp, overdamp, and we have another one called underdamped. The underdamped case, underdamped, damped case. In the underdamped case, we have the situation when in this case we have a situation when alpha is less, right? So alpha is less than omega naught, right? Now let's think about that. So if we have something like this, if we have S1 is equal to minus alpha plus or minus, right? Plus or minus alpha squared minus omega squared. What happened here if over here when alpha is greater than omega, right? So in this case, we have an over-damped, under-damped case, right? And that happened when the inside the square root becomes imaginary case, right? That becomes an imaginary case, which now we're talking about sine and cosine. Now we're talking about trigonometry getting involved in this, right? And that is when we have an imaginary number inside, right? Now there is some graphs that probably not gonna have a time to do it today, but that explain the damped, the underdamped case, the overdamped case, and the critical damped case. So this is underdamped, right? When omega is greater than when omega is greater than alpha. Yep. So in this case, as you can see, the even number gets bigger, right? If this number gets bigger, it's going to be a negative number inside the square root, and then it's going to create a negative number, which means that we have an imaginary number, which is, it will create two different roots, and those two different roots